or afternoon, I guess, depending on when you're going to watch this video. It's the day after our little Veterans Day break on October 12, 2014. Today, we're going to be talking about the last section in Chapter 2, which is the constant rate of proportionality. And before I begin, let me just go ahead and apologize for the way I sound. I'm not French today. I am feeling under the weather, kind of ill and congested. So please bear with me if my breathing is off, I sound like Darth Vader, or if I seem to have an accent of some kind. So, moving on. We're going to begin on page 195, and we're talking about our last section in Chapter 2, Proportions, and more specifically, we're talking about the constant of proportionality. Now, this is another name, once again, for the same kind of thing we've seen over and over and over again. And let's go ahead and just jump right into this real-world example. Here it says the distance d a car travels after t hours can be represented by d, distance, equals 65 times t. The table and the graph also represent the situation. Let's investigate the relationship between distance and time. So here we have a nice table and a graph to match. We have time measured in hours and how far we go, the distance measured in miles. On this graph we have the same things. Time is on the x-axis and distance is on the y-axis. We have several points that have been noted both in our chart and in the graph, and those points represent at certain times how far we've gone. For example, in 2 hours, we've gone 130 miles. In 3 hours, we've gone 195 miles. And in 4 hours, we've gone a total of 260 miles. So our first instruction here is to determine the constant ratio. So we're going to take how far we've gone, the distance traveled, and divide it by our driving time. Or actually write it underneath our driving time. So we have 130 miles in 2 hours. If we look at our graph, we know we go at 195 miles in 3 hours, and it also says it over here in the table. So I'll go ahead and write a 3 in there. Then I have the reverse data here. If I go 4 hours, how far have I gone? 260 miles. It also tells us in our table above. Well, so far, so good. Now, what we're going to do is take each one of these ratios and divide them to see what we get. 130 divided by 2 is going to be 65 over 1. 195 divided by 3 is also 65 over 1. And 260 divided by 4 is, you guessed it, 65 over 1. So we have equivalent ratios, which means they are all related, all proportional. And our constant ratio then is we are traveling at 65 miles per hour, or per letter t. Right here, that's pretty obvious. In 1 hour, we've gone 65 miles. That would be the point we have right there if we were to continue making this graph. And the further we go on in time, the further we go on. As long as we don't stop for gas or stop at all totally, we can keep going like that indefinitely. Instruction number 2 says, determine the constant rate of change. So we're going to take how much we changed in miles and how long we've changed in time. So let's go ahead and look at, whoops, there we go. When we have the same exact thing again. You take how far you've gone, 260 miles, you divide it by 4, and you'll get the same exact thing all over again. You're going to get 65 miles per hour. Now they want us to write in the instructions on the third one down here, write a sentence that compares the constant rate of change and the constant ratio. Okay, well we can say the constant rate of change is 65 miles per hour. We know that the constant ratio is also 65 miles per hour. So they're both the same, and our book tells us that right here. So that's just the introduction to constant rate of change. Let's go ahead and move to the next page, 196, and begin with our examples. So we have in the very beginning, it's called direct variation. This is a really big idea for algebra and here on up. And basically what the direct rate of change tells us, and here they give us the definition, it's a relationship is a direct variation when the ratio of y to x is constant, k. We say y varies directly with x. I know that's kind of upper level to understand, but maybe the example or the equations here might help you. If you have something divided by another number that gives you the same thing, or if you keep multiplying x times the same number k and you keep to get different numbers, you have direct variation. Let me give you a better example, and it might make more sense when we read it down here. So when two variable quantities, that's two things that we don't know, have a constant ratio, the relationship is called direct variation. Another way you guys might understand it is when we have something that is the product of some mystery number always being multiplied times whatever they give us we'll get an answer. So basically, as long as we're always multiplying by the same thing over and over again in any table or chart, we have direct variation. It also works with, you guessed it, division. When you divide two numbers, and if you always get the same answer over and over and over again, you have direct variation. An example of that over here might be, let's work up here first. Let's say I have y equals 3 times x. That means whatever I put in for x, I'm always going to multiply it by the same number, 3, to get an answer. No matter what I put in here, it's always being multiplied times the same exact thing. That thing is called a constant. Here they write it as the letter k. For division, it works the same way also. If I have numbers, let's say 10 divided by 2 gives me 5. Or I have 20 divided by 4 gives me 5. If I divide numbers and I always get the same thing over and over again, then I also have a constant of variation. And it's also called, because in math, I'm not going to lie to you, we give many times the same thing a bunch of different names. So we also call this not only the constant of variation, but it's also called the constant of proportionality. They're the same exact thing. How much is something always changing by? And we're going to practice discovering that and calculating it in this first example down here. Now, let's go ahead and read our side note. When a relationship varies directly, so when you have, in other words, direct variation, and you may want to write that down because you have to know that phrase, direct variation, which is also the title of our chapter. When you have this, the graph will always go through the origin 0, 0. So there's a big, huge, like red flag sign for you. It has to go through 0, 0. It looks like a little face I drew almost. Or, in other words, the origin. Okay, and the unit rate is located at 1 something. So that means if I go to x equals 1 on my graph, whatever answer I get for y will be the unit rate. And we're going to hopefully discover that in this first example. So here we have the height of the water as a pool is being filled is shown in the graph. Determine the rate in inches per minute. So here we have how much water is being filled in the pool. 2, 4, 6, and 8 inches. On the bottom, we have how many minutes has gone by. 5, 10, 15, 20, and 25. And then we have a graph. This graph shows how high the water level was in the pool at various times on this graph. So it says here, since the graph of the data forms a line, the rate of change is constant. So that's another big sign we need. We have to get a straight line. Or in other words, our graph should be linear, L-I-N-E-A-R. Use the graph to determine the constant of proportionality. So we're basically going to take all our ratios. And our ratios, the way we write them is we take our second coordinate and put it over the first one, or the y over the x. So even though I know this is read as 5, 2, I will write my ratio as 2 over 5. Over here, my points are 10, 4, but I'll write that ratio as 4 over 10. Over here, my points are 15, 6, but I'll write the ratio as 6 over 15. And I'll follow the same process over here for the last point. Now, these ratios are also fractions, which means they can be simplified. Simplifying is always what you want to do to check if you have a constant ratio, a constant rate, a constant of proportion, whatever you want to call it, direct variation even. So I'm going to divide 4 and 10 by 2, and I get 2/5. Whoops, make my 5 a little better. There we go. 6 and 15, I'll divide those both by 3, and lo and behold, I also get 2/5. 8 over 20, I'm going to divide both of those by 4, and I get 2/5. Everything matches. So because I have the same ratio of height to time, and they just have the work done again for us down here, 2 to 5. And here what they did, you're wondering where they get this 0.4 over 1. Because in order to determine the rate in inches per minute, I have to know how much water I have for 1 minute. And these ratios tell me how much water I have in inches for every 5 minutes. So the way you do that is then now you have to divide because you need to have a 1 on the bottom to basically get a unit rate. This is what a unit rate is, the same thing as the constant proportion. So finding the unit rate is always going to be important. I'll take my smallest fraction, the 2/5, and I'll go ahead and divide it. I know 5 will not go into 2, but it will go into 20 4 times. I have no remainder. Therefore, 2 inches every 5 minutes is the same thing as 0.4 inches every 1 minute. So I have my unit rate, or my constant of proportion. It's all the same thing. These are all the same words over and over and over again. Use this example now to help you do got it letter A. Go ahead and work that on your own, And make sure you ask any questions if you're confused before we actually assess it. Let's move on to page 197 now. We have example 2. It says the equation y equals 10x represents the amount of money, which we'll call y, Julio earns for x hours of work. Identify the constant of proportionality. And that sounds very important, so I'm going to go ahead and circle all this. Constant of proportionality, that's what they want us to do. Identify it. Explain what it represents. So not only do I have to identify, I also have to explain. Very easy. First of all, something's proportional if you're only multiplying and dividing. I have the equation y equals 10 times x. So first of all, I know I have multiplication happening right here. I have no addition or subtraction going on. So I know, all right, that's good. That's a good first sign. Now, I also know that whatever it is I'm multiplying by is going to be my constant of proportionality. Well, everything that I plug in for x, because x could be any number, remember, is always going to get multiplied times 10. So my constant of proportionality, which we'll call letter k, is going to be 10. Oops, my pen kind of froze here a little bit. There we go. K equals 10. Okay, I identified my constant. That was easy, but now I have to explain what it represents. Well, it tells me in the story that the amount of money y Julio earns, so this is money, and it says it depends on how many hours of work, x. So this is hours. So 10 must then represent how much money an hour Julio makes. Another way I can prove that mathematically is I want to get 10 all by itself. I have y equals 10 times x. Well, I want to do the inverse of multiplying times x, which would be dividing by x. When I do that, I get y over x equals 10. This was the formula we saw in the previous page on the top. It says to get your constant proportion, you take your y divided by x, and whatever you get is your answer. So $10 an hour is basically what Julio charges. And you could see that. It makes sense. $10 every single hour he works will tell you how much money he makes. It's very easy. It looks more complicated than it really is. At this point, go ahead and try got it, letter B. And as always, make sure you ask for help or clarification as you work it out, if you need it. Finally, our last topic in this section is determining direct variation. Now, there's different ways to find direct variation. And it says here, not all situations with a constant rate of change are proportional relationships. That was a fact we stressed a lot this last 2 weeks. Multiplying and dividing is always a good sign you have proportional relationships. We like that. But just because you multiply and divide does not mean you necessarily have a proportional relationship. In other words, they're not all direct variations. I want to kind of emphasize that right there. Not all. Just because you multiply and divide is simply not enough information to determine if you have a direct variation. And we're going to explore that right now in example 3. So here it says pizzas cost $8 each plus a $3 delivery charge. Show the cost of 1, 2, 3, and 4 pizzas. Is there a direct variation? All right, I want to break down this whole sentence before I even go any further. I have $8 each. Right there, that's a unit rate. I'm paying $8 for one pizza. And we know a unit rate's always necessary when you have direct variation or a proportional relationship, in other words. But it says here, plus a $3 delivery charge. Big rule. We are never adding or subtracting when we have proportional relationships or direct variation. So I don't like that right there. That's already going to be like a bad sign that this is not going to work for me. I'll put a little sad face there. Now it says show the cost. So we have this table here. One pizza costs $8 plus $3 for delivery. That's 11. 2 pizzas, that'd be $16 plus 3 is 19. 3 pizzas would cost $27. 4 pizzas at $8 a piece would be $32 plus the $3 delivery fee. That's $35. So we have multiplication going on, but we also have this delivery charge, which is kind of fudging everything up. And as I explore this, I'm going to go ahead and look at the ratios. Now look, we have a nice little graph. 1 pizza 11, 2 pizzas 19, 3 27, 4 35. We know we need to have a linear or straight line. That's very important, but it's not the only evidence we can use. It has to go through where? And if you remember, it has to go through here, the origin. And we could see it's very obvious this line does not go through the origin. So there's another bad sign that's not going to work out for us. Finally, let's prove it mathematically. Let's take all our ratios. So the easiest one I have is right here, $11 for one pizza. Then I have $19 for two pizzas. Then I have $27 for three pizzas. And then I have $35 for four pizzas. I'm going to simplify all those fractions. 19 divided by 2 gives me 8.5 over 1. That means each pizza here was about $8.50. Actually, that's a little off. I'm sorry, my math is totally off there. It's about $9.50. Excuse me. We'll chalk it up till I'm sick. Yeah, that's what we'll say. Here, for $27 for three pizzas means we're spending about $9 a pizza. And then the $35 for four pizzas means we're spending about $8.75. Everything I just did is still here in the example notes. So it tells us right here, since there is no constant ratio, because everything should be 11 to 1, which we do not see here. We don't have a constant ratio. Our line, which is linear, does not go through the origin. We are adding in our description here, all those are red flags that we do not have a direct variation. So knowing that now, go ahead and work out got it letter C. They give you a chart and a graph, everything on the side they need you to fill out. So please fill out all three components before answering your question. They want you to not only show the cost of all these pounds of cheese, but also if there's a direct variation, they want you to find it. If there is or is not, explain how you know your answer. You got quite a bit to do in this problem, and that's good because this is the culmination of everything in this chapter. This will show if you really understand what's going on before your test. And finally, we're going to go to the next page, which is our last example. Thank God, because I'm getting a little tired of talking, and I'm sure you're getting tired of hearing my voice. So here we go. Last example, example 4. Determine whether the relationship is a direct variation. If so, state the constant proportionality. So first, we have to determine if we have direct variation. And then, if so, what is the constant? So let's look at our table here. I have 112, 224, 336, 448. These are all easily identifiable because I know my times tables as just being multiplying times 12. So 12 to 1, 24 to 2, 36 to 3, and 48 to 4. This is already simplified in lowest terms. This simplifies to 12 over 1. This simplifies to 12 over 1 because I divide everything in this case by 3. Here I divide everything by 4, and I still get 12 over 1. Since I have equivalent ratios, I know that I have direct variation. The direct variation is going to be everything up here is getting multiplied times 12. So my constant in proportionality, my letter K, is 12. Very easy. This was the easiest one to do of all. I know automatically that if I'm multiplying something in the x to get the y down here, if it's the same every single time, you automatically have direct variation. You automatically have a proportional relationship. You automatically will have a constant proportion. It's that easy. These are a lot of big words to take in, and that's probably the hardest part of this section, but it's very easy conceptually what you're doing. If you're multiplying or dividing by the same thing over and over and over again, and never adding or subtracting, then you will have proportions. All right, go ahead and work on the guided practice now. You need to work on examples 1, 2, and 3, please. You will be assigned homework later on in class. Thank you very much.